Have you ever just stopped and thought about the incredible raw power churning away just miles beneath your feet? Well, today we're diving into the science of earthquakes. We're talking about the colossal forces that literally shape our world and can, in just a matter of seconds, reshape our lives. So let's get right into it.
I mean, it's the ultimate question, isn't it? We kind of take it for granted that the ground under us is, well, solid. So why in the world does it sometimes shake, rattle, and roll with such terrifying force? That's the big mystery we're going to unravel today.
So, at its most basic level, this is what an earthquake is: a sudden, super violent release of pent-up energy. Think of it like a lightning bolt, but instead of flashing through the sky, it rips right through solid rock. And to figure out where that incredible energy comes from, we need to zoom way out and look at our planet's basic design.
Right, because all this shaking isn't random. Not at all. It's actually part of this epic, planet-wide system, a giant geological engine that's been constantly changing the face of the Earth for billions of years. Let's pop the hood and take a look.
Okay, so to really get a handle on earthquakes, we've got to understand the Earth itself. We have to, peel back the layers, literally, to see the engine that's driving all this incredible activity.
And this is just a perfect way to think about it. Picture the Earth as a giant peach. In the middle, you've got the pit. That's our planet's super hot core. Then there's the fleshy part, which is the mantle, this huge layer of rock that's so hot it actually flows like super thick honey over millions of years. And the skin? Well, that's the crust, the thin, fragile surface we all live on.
And here is the absolute key. That skin, the crust, it's not one solid shell. It's actually shattered into these massive slabs we call tectonic plates. And these giant puzzle pieces are constantly drifting around on top of that gooey mantle, moving about as fast as your fingernails grow.
So as these plates are moving, their edges, what scientists call plate boundaries, that's where all the action is. They can smash into each other, creating huge mountain ranges like the Himalayas. They can pull apart, creating new crust on the ocean floor. Or, and this one is a big deal for a lot of earthquakes, they can just grind horizontally right past each other. Okay, but that brings up a really good question. If the plates are always moving, why isn't the ground always shaking? What causes that sudden violent snap? Well, the answer comes down to one simple word: friction.
Just rub your hands together really fast. You can feel that heat, that friction. Now, imagine that same force, but on a continental scale. The edges of these plates aren't smooth at all. They're jagged and rough, and they get snagged and locked onto each other with an absolutely unimaginable amount of force. And this process right here is the heart of the whole thing. So while the edges are locked solid by friction, the rest of the giant plates keep pushing forward relentlessly. All that force has to go somewhere, so it gets stored in the rock, bending and stretching it just like a rubber band. The tension builds and builds and builds until finally the stress is just too much. Snap! The friction gives way, the fault ruptures, and all of that stored up energy is released in a matter of seconds. That is the earthquake. Okay, so here are two terms you always hear, and it's easy to get them mixed up. The hypocenter or focus, that's ground zero, the exact spot deep inside the Earth where that snap actually happens. Then you have the epicenter. That's the point on the map, right on the surface directly above the hypocenter. It's usually where the shaking feels the strongest. Now, that massive burst of energy doesn't just stay put. It radiates outwards from the hypocenter in all directions as waves of motion traveling through the rock. It's exactly like when you drop a stone into a still pond and watch the ripples spread out. Those ripples, they're the seismic waves that make the ground shake. So if an earthquake is just these energy ripples moving through the planet, how in the world do we see them? How do we measure something so powerful happening miles and miles beneath our feet? Well, this is where the amazing science of seismology comes into play. This is a brilliant analogy. Think of an earthquake like a thunderstorm. First, you see the lightning, then you hear the thunder, right? It's the same idea. The first waves to show up are the P waves, or primary waves. They're the lightning. They're super fast, and they travel by pushing and pulling the rock. Following right behind them are the S waves, or secondary waves. They're the thunder, slower but way more destructive, shaking the ground up and down or side to side. And that time gap between the lightning and the thunder, the P and S waves, that tells scientists exactly how far away the earthquake was. So how do we actually record these waves? We use an instrument called a seismograph. And the concept behind it is just brilliantly simple.
You have a really heavy weight that's suspended so it can hang freely. When an earthquake hits and the ground shakes, the whole machine moves with it, but the weight, because of inertia, stays almost perfectly still. A pan attached to that still weight then draws a wiggly line on a moving roll of paper, literally drawing a picture of the Earth's vibrations.
And you can actually see this for yourself. This is such a cool experiment. You just get a box, hang a marker in it, and have a friend shake the box back and forth while you pull a strip of paper underneath. The marker, hanging still, will draw the earthquake for you. A little shake makes little wiggles. A big shake makes giant wiggles. Bam! You've just made a seismogram. All right, this brings us to another really important distinction that people mix up all the time: magnitude versus intensity. Magnitude measures the total energy the earthquake released right at the source. It's one single number for the whole event, like a magnitude 6.5. Intensity, on the other hand, describes the effect of the shaking at a specific place. The very same earthquake will have a super high intensity near the epicenter and a really low intensity far, far away. Now get this, because this part is kind of hard to wrap your head around. The magnitude scale is not like a ruler, it's logarithmic. What that means is for each whole number you go up, the ground shaking is 10 times stronger. But the energy released, that jumps up by about 32 times. So a magnitude 7 earthquake isn't just a little bit worse than a 6, it's a completely different animal. It's a monster. So to put all that into perspective, this was the magnitude of the largest earthquake ever recorded. It happened in Chile back in 1960. The amount of energy released by a 9.5 is it's almost impossible to comprehend. This number represents the absolute peak of what our planet's tectonic forces can throw at us. Okay, so we've looked at the science, we've measured the immense power, now we get to the most important part. What does all of this mean for us, living on this very active planet? Because turning all this knowledge into action, that's the real key to staying safe. You see, the danger from an earthquake isn't just the shaking itself, though that's obviously terrifying. The ground can literally split open. Quakes that happen under the ocean can move huge amounts of water, creating devastating tsunamis. All that shaking can trigger massive landslides. And of course, broken gas and power lines can spark fires that spread all over the place. And this activity isn't just happening randomly all over the globe. It's really concentrated along those plate boundaries we talked about earlier. About 90% of all earthquakes happen in this massive horseshoe-shaped zone around the Pacific Ocean, called the Ring of Fire. It's where the giant Pacific plate is interacting with a whole bunch of other plates, making it the most seismically active spot on Earth. So, if you ever feel the ground start to shake, I want you to remember these 3 simple words: drop, cover, and hold on. Drop to the ground, cover your head and neck by getting under a sturdy table or desk, and hold on tight to your shelter until the shaking stops. This simple action protects you from falling objects, which is the #1 cause of injury. It is, without a doubt, the single most effective thing you can do to keep yourself safe.
And really, that's our final crucial takeaway here. As of right now, science cannot predict the exact time and place an earthquake will strike. But what science has given us is the power of understanding. We know where they happen, we know why they happen, and we definitely know how to be ready for them. That preparation is our greatest strength. So the only question left is, are you ready? Thanks for joining me.